Settle in, friend. Let the room grow quiet and kind around you, the edges of the day softening like moonlight on water. Breathe a little slower. Feel the mattress welcome your weight, the heartbeat of the night, steady and calm. Tonight we drift with a traveler made of mirrors and gold, the James Webb Space Telescope, gazing so far into the dark that light itself arrives as a memory. It looked deeper than we expected, and what it found felt startling at first, like discovering a lantern glowing in a forest you thought was empty. Surprises bloomed in the silence, ancient galaxies wearing the brightness of youth, newborn structures arranged with puzzling grace, whispers from the first dawn of time. We won't hurry. We'll let each idea unfold the way stars reveal themselves when your eyes adjust to the dark, quietly, patiently, without strain. If these gentle voyages help your evenings feel softer, you can tap like or subscribe whenever it's easy. That simple ripple helps other sleepy minds find their way here. For now, let your breath move like tides, in and out, while we follow faint starlight across the black curiosity in one hand. Rest in the other, listening for the universe as it hums itself to sleep. Out in the cold darkness, where distances are counted in billions of years, and light arrives like messages from a much earlier sky, the James Webb Space Telescope keeps watch. Its mirrors gather the faintest embers and carry them home, not as alarms, but as quiet puzzles. What returns to us is not chaos, but a hush filled with questions, ancient galaxies shining as if they had grown up too fast, black holes already heavy in a universe still blinking awake, murmurs from wandering worlds that drift without suns. None of it needs to frighten us. It asks us, gently, to listen longer. For a long time, we thought we understood the pace of the cosmos. Imagine the universe as a calm tide, lifting every boat with the same slow breath. Astronomers measured that lift in two different ways and expected the numbers to agree. One approach reads the flicker of special stars called Cepheids, steady cosmic lighthouses, whose brightness tells us how far they are, and therefore how fast space between us grows. Another approach listens to the afterglow of the first light, the faint microwave hush left over from the universe's hot, bright beginning. 2 yardsticks, 1 ocean. But when the Webb telescope joined the listening, the tide felt uneven. The measurements that had been politely disagreeing began to sound more certain in their disagreement. The Cepheid yardstick suggested one rate of expansion. The ancient afterglow suggested another. The two answers do not meet in the middle. They keep their distance, like two stars in different orbits. Astronomers call this the Hubble tension, a tidy name for a persistent itch. It is not a matter of bumping the telescope or smudging a lens. Teams have checked and rechecked thousands of stars across many galaxies. The contradiction lingers, like a tone you can still hear after the bell has stopped ringing. What could make a single universe tell two stories about how quickly it opens? Perhaps our picture of dark energy, the subtle pressure that encourages space to stretch, is incomplete. Perhaps it changes its character from one era to another, or from place to place, the way wind can slip through valleys and slow at a ridge. Perhaps our equations, beautiful and brave, are missing a small piece that becomes large when spread across everything. None of these ideas are accusations. They are invitations. A universe that resists simple answers is not misbehaving. It is teaching. If that were all Webb had brought us, it would already be enough to make textbooks soften their edges. But the mirror kept drinking in starlight. and the deep fields, those small squares of sky chosen precisely because they look nearly empty, began to fill with surprises. Near the familiar curve of the Big Dipper, pixels that should have been modest, glows turned out to be something else. Compact, red-tinged smudges that held far more light than their size would suggest. Red in astronomy is often the color of distance, the footprint of light stretched by expanding space. These smudges were distant, yes, and yet they were also too bright, too organized, like saplings that somehow had the shade and mass of old oaks. One researcher, scanning the images piece by tiny piece postage stamps of the early universe, noticed these unlikely embers and paused. They did not look like the fragile first drafts of galaxies we had rehearsed in our minds. They looked mature, busy, already hosting vast populations of stars when the cosmos was only a few % of its present age. To reach such stature so quickly, each would have needed to knit hundreds of suns every year for long stretches of time, while our own Milky Way, comfortably middle-aged, manages only a couple in a typical year. Picture fog becoming frost in a heartbeat, dew gathering into a river before the morning is over. The numbers are simple but astonishing. Some of these early systems may hold 10 billion stars, some perhaps nearer to 100 billion masses that belong to big city galaxies, not small frontier towns. Models had told us the early universe should assemble its structures like careful builders, start small, merge slowly, add rooms and corridors over eons. Yet here we were, looking at skyscrapers rising while the blueprints were still on the table. Colleagues teased them with nicknames, hinting that they could break our current universe-building rules, not because nature is violent, but because our instructions may need revision. What would help such rapid growth? Invisible scaffolding dark matter could have gathered more quickly than we expected, cradling gas in deep wells where gravity could work faster. Streams of pristine hydrogen could have flowed in steadily, feeding star formation at a relentless pace. Perhaps early stars were more efficient at turning raw material into light, their first generations bulkier and brighter, seeding their neighborhoods with heavy elements that encouraged further growth. None of these thoughts are pronouncements. They are lanterns we set along a path so we can keep walking without tripping over our certainty. The red light that drew attention to these galaxies is not an alarm either. It is the color of distance and time, the soft tint that long travel paints on ancient photons. When that light arrives, we catch it like snowflakes on a sleeve and study the patterns. Spectra rainbows stretched thin tell us what elements glow within, how quickly the systems are moving away, whether dust dims their hearts. In the quiet of the data, there is the sense of being let in on a secret. Complexity appeared early. Structure had a head start. This early complexity folds back into the question of the universe's pace. If structures grew faster, maybe our assumptions about the smoothness of space's expansion need tuning. If the expansion has been the same everywhere and for all time, then the recipes for making galaxies must be far more efficient than we imagined. If, instead, the expansion or the behavior of dark energy has varied subtly with age or location, then both the Hubble tension and the speedy rise of these giants may be verses in the same song. Either way, no law of physics is being thrown out of the house tonight. Laws bend to better fits when the evidence asks them to, the way a sail shifts to catch a shifting wind. The story also brushes the edges of black holes, those concentrated wells of gravity that hide their interiors with perfect modesty. In the same early times, Webb and other observatories are finding signs that some black holes put on mass quickly. radiating fiercely as matter spirals inward. This does not mean they are older than time. It means time in those neighborhoods was busy. Perhaps heavy stars collapsed directly into large seeds. Perhaps clouds fell in without cooling, forming deep wells from the start. When we think of impossible, it is often our intuition that needs rest, not the universe. All this talk of riddles and revisions can sound urgent in daylight. At night, under a blanket, the urgency falls away and the wonder remains. The cosmos has always surprised us. It startled ancient eyes with wandering planets, startled sailors with new stars rising at unfamiliar angles, startled physicists with the idea that empty space can carry energy. Surprise is not a flaw. It is how reality keeps us awake to its beauty while it lulls us to sleep. So let the two yardsticks keep their gentle argument while we learn to read them better. Let the early galaxies glow with their improbable vigor while we revisit our blueprints and test fresh physics against old light. There is a kindness in this process. Patient instruments, patient minds, patient time. The Webb telescope does not demand instant answers. It opens a door and stands quietly to the side while we step through. Imagine, now, those 6 ancient structures resting in the young darkness, each a city of stars thrumming with newborn light. Gas weaves inward along filaments. Dust settles into disks. Clusters bloom like neighborhoods after rain. Supernovae spark and fade, scattering metals that future worlds might need. Somewhere, a black hole sips from a bright whirlpool, not voracious, just steady, a metronome for the galaxy's heart. The pace is quick compared to our expectations, but it is not frantic. On cosmic scales, even haste has the patience of mountains. If you hold the whole picture softly, expansion that needs a new lyric, galaxies that grew up early, gravity doing its intricate work, the scene becomes calming again. We are not watching a universe break itself. We are watching it reveal more of its face, like a friend who, after years, shares a story you had not heard and suddenly makes previous stories make more sense. The thrill is not in the shock, it is in the coherence we have yet to write. Let the mind float with that feeling. Out beyond the Big Dipper's familiar curve, beyond the seasons and the weather and the day's small concerns, those red-tinged smudges keep whispering. Their light crossed a wilderness to find us. It asks no drama. It asks only that we breathe a little deeper, listen a little longer, and accept that even in the earliest dawn, complexity was already practicing its music. The universe, it seems, learned its rhythm early, and only now, in the quiet, do we begin to hear it. To know whether those bright, compact smudges are truly galaxies and not something masquerading as them, astronomers reach for a quieter tool than an image. They spread the light into a thin rainbow and listen for the small signatures hidden inside. A spectrum is patient. It tells you how far the light has traveled, by how much the lines shift, and it whispers what elements glow within. Webb spectrographs do this work like careful librarians, laying every photon on the table so its history can be read. Follow-up studies began to sort imposters from the real thing, and the patterns that emerged were stranger and lovelier than many expected. Some objects, once their light was unbraided, did not look like sprawling star cities at all. They looked like single compact engines points rather than neighborhoods pouring out luminosity from regions far too small to be galaxies. The early universe, it seems, had more kinds of lanterns than we thought. In that quiet sorting came a presence so concentrated it felt like a held breath. A black hole, heavy as 50 million suns, traveling almost alone, no bustling host galaxy around it, no great spiral of stars to advertise its address. Most supermassive black holes live in the bright centers of galaxies, anchored there like hearts, their gravity orchestrating the dance of stars and gas around them. This one appeared more like a solitary pilgrim, a deep well moving through the dark, with only a thin, hot veil of infalling matter to outline its silhouette. Its nickname in the literature is a string of letters that sound like a whisper. You can imagine it as a quiet question set against the first dawn. The scale is hard to hold. Compress the mass of tens of millions of suns into a region smaller than our solar system, and you get a gravity so intense that even light, the great traveler, cannot leave once it steps over the edge. That is familiar black hole territory. What unsettles our intuition is the timing. This wanderer was already heavy when the universe was only about 600 million years old, an age when our mental picture prefers small, early clouds, tentative stars, delicate filaments just beginning to braid together. To arrive so soon with such weight suggests a path we did not plan for. When something refuses to fit the script, we do not scold the cosmos. We revise the script. One gentle revision says some black holes may form not from the ashes of stars, but from the direct collapse of giant gas clouds. If the conditions are right, metal pour, gas, intense inflow, ways to shed heat so collapse doesn't stall, gravity can tighten the cloud without stopping to build a star in the middle. Another possibility is that medium-sized black holes, born from the first massive stars, grew with unusual appetite, feeding faster than the tidy limit we often assume, their disks thick and turbulent, their radiation leaking in directions that allow the banquet to continue. A third idea leans further back toward the first seconds and imagines that a few black holes were seeded by the universe itself, condensed from the raw fluctuations of energy and curvature before chemistry, before stars, before anything with a surface. These are called primordial black holes, and thinking about them is like thinking about fossils laid down before life. Hold those 3 lanterns up and the road looks less daunting. Direct collapse gives us heavy seeds early. Exceptional growth gives us quick steps between rungs. Primordial seeding gives us a head start that is measured not in centuries, but in the clock of creation itself. None of these is a drama. Each is a way to let gravity do what it does, with slightly different starting conditions. The early universe may have offered more lanes onto the highway than the late universe does. Nature is thrifty like that. Use what is available. Build with what the moment allows. As spectrographs continued to sing their thin songs, more red points appeared. They dotted the deep field like embers, each one a compact blaze whose light flickered with the telltale cadence of matter, spiraling inward and heating as it fell. From far away, an accreting black hole can mimic a small galaxy. Because both are bright, it takes the fine print of spectra and the shape of the light to tell them apart. Many of these points were not sprawling towns of stars. They were lighthouses, tiny, bright cores shining because gas was being warmed to incandescence near an event horizon. If that is what many of the earliest beacons were, then part of the young universe's glow came not from stars at first, but from gravity's kitchens. This thought dovetails softly with the puzzle of giant black holes appearing so early. If some black holes were present from the beginning, primordial in the plainest sense, then they would have waited in the dark like seeds waiting for rain. When the first gas condensed, there they were, already prepared to feed. Accretion is a patient process across cosmic time. Gas drifts in, heats, radiates, and the black hole gains mass grain by grain. breath by breath. Give a seed a head start of hundreds of millions of years, and the size we see at 600 or 400 million years after the beginning is no longer outlandish. It is simply what steady meals can do over long intervals. This picture opens a quiet door onto our own neighborhood. If primordial black holes were made in any abundance, some fraction may still roam the modern universe invisibly, rarely announcing themselves unless they pass through a cloud or lens the light of a background star. The thought is not menacing. These would be small, dark wanderers among innumerable stars, part of the furniture of space, not predators. It is an idea to carry like a smooth stone. The present is full of relics that remember the first moments. Even as we absorb this, Webb's gaze and the layered attention of other observatories drew us to a different kind of drama, one that looks like a symbol you might draw when you're daydreaming. Two compact, red cores with halos of light trace a figure eight, a gentle loop meeting itself in the middle. It is a pair of colliding disk galaxies engaged in a head-on conversation. Galaxy encounters are common over long timescales. Gravity likes to gather, and orbits bring neighbors close. Usually, the result is a merging that scrambles spiral arms and gradually funnels the central black holes together until they marry, or one is flung away. Here, though, something more intricate is unfolding. Between the two luminous hearts floats a third concentration, a black hole, not seated in a galactic center, but poised between them, embedded in a river of glowing hydrogen. Imagine two mountain valleys whose rivers meet and churn between their slopes. In that mingling, eddies form and weight can collect. The streams of gas stripped from each galaxy by tides have pooled in the middle, and conditions there, density, cooling, a hush against fragmentation may have let gravity fall inward directly. That is the essence of direct collapse, played out not in the solitary quiet of a pristine cloud, but in the wake of an encounter that stirred and thickened the medium. The black hole is not hovering by magic. It is sitting where the flow favors it. Radio measurements and infrared spectra mark the place where matter is being heated and funneled down. The core feeds as the galaxies continue their slow pass through one another, and the figure eight glows not with disorder, but with a new kind of order. Two ancient structures maintaining their identities, while midwife to a third. This scene turns the thought of direct collapse from abstraction into choreography you can almost see. Gravity does not always build only through the deaths of stars. Under the right music, collapsing gas can skip steps and go straight to a deep well. The beauty of this is not in breaking rules, but in expanding them. Early black holes that grew too fast by our first estimates stop looking like rule breakers if we allow both these paths, primordial seeding and direct collapse, to contribute. A cosmos with multiple ways to make its compact objects is not chaotic, it is robust. The young universe would have been full of colliding streams, cooling patches, tidal tails, and bright knots where flows met. In those knots, stars burst alive. In some, if the conditions prevented the gas from fragmenting into many small pieces, a single deep collapse could light the center. You can think of it as weather. Sometimes clouds gather into drizzles of small drops. Sometimes a single storm cell swells and pours. We watch this with instruments, but we also watch it with patience. The infant cosmos does not shout its biography. It allows us to infer it from a long trail of light. The point-like sources that speckle the deep fields, the figure eight that sketches a symbol for endlessness, the solitary wanderer with a mass that presses on thought, all are pages in that trail. Spectra help us sort the punctuation. Broad lines suggest fast-moving gas near a black hole. Narrow lines hint at calmer star-forming regions. Breaks in the rainbow tell us which elements are present and how far the light has traveled. Behind the techniques runs a single feeling. The early universe was not only busy, but inventive. This inventiveness was not violence for its own sake. Collisions and collapses in space do not have the malice the word crash suggests to our daylit minds. They are exchanges of momentum and energy, choreography and slow motion. When two galaxies intertwine, stars mostly pass by stars without meeting. It is the vast pools of gas that feel the tides. Those tides can feed central engines or trigger waves of star birth that sweep through a disk like spring through a field. The process can look wild in a snapshot. In its own time, it is as steady as geology. Bring your attention back to the naked black holes, those red points that betray their presence by the way they shine. The light we see is not from the holes themselves, which keep everything that crosses their thresholds. It is from the matter just outside, rubbing against itself in a hot, bright spiral before it falls in. That glow can flicker on short time scales compared to the universe's age, days to years, rather than millions of years. And those flickers will help us tell one source from another. Over time, we will learn which of the early lights are compact engines and which are compact starbursts. The answer will likely be many or both in changing proportions, because the universe does not choose a single melody and play it forever. All of this folds back into how we think about growth. A black hole of 50 million suns by 600 million years is startling when you imagine a single path to that mass. It is calmer when you imagine several. Seed heavy, grow efficiently in thick disks, and let the environment cold streams, galaxy encounters, quiet cooling do some of the work. In the same way, those 6 early massive galaxies are less alarming if we allow that their scaffolding of dark matter may have been deeper than we assumed, gathering gas quickly and holding it while it formed stars. Letting the universe be good at building removes the drama without removing the awe. The figure-8 system adds a last, soothing note. Seeing a black hole in the bridge between two galaxies suggests that collision-born clouds can make direct collapse not just a theoretical path, but an active one. If that was true more often in the past, then the abundance of early supermassive black holes is no longer a paradox. It is the natural result of a universe that learned to turn converging flows into anchors. Those anchors, in turn, shepherded the growth of the galaxies we see later, not as tyrants, but as centers of quiet gravity that help keep the dance in time. As you drift with these images, let the harsh words of impossible and disturbing melt into gentler ones, unexpected, instructive, generous. The cosmos is not misbehaving when it offers multiple ways to arrive at the same destination. It is showing us that our first sketches were too simple, that complexity arrived early, and that gravity, given time and raw material, is a master craftsman. Webb's gift is not only in the sharpness of its eyes, but in the spaces it opens for thought, a little more room for early black holes to be born in the flow between galaxies, a little more room for seeds set at the beginning to bide their time, a little more room for light to come from places we once would have overlooked. Breathe with that. Somewhere beyond the Big Dipper's outline, 2 old disks continue their slow embrace. Between them, a third presence gathers itself from the shared river, feeding in soft, invisible spirals. Elsewhere, a lone mass, heavy as a song you can feel in your ribs, walks the dark, with nothing but its thin scarf of hot gas to give it away. In far corners, red points flicker engines practicing the first arias of light. The universe is not broken, it is rich, and in the quiet, it lets us learn its richness at the pace of our breathing, one spectrum at a time, one soft revelation after another. Far from the crowded lights of stars, in the velvety lanes of a stellar nursery, small wanderers drift like dandelion seeds on a night wind. They are worlds without suns, cool and unhurried, each the size of a giant planet and each carrying its own quiet story. Webb's deep gaze into the Orion Nebula revealed hundreds of these travelers, and a surprising number are not alone. They move as couples, circling one another at distances so wide you could lay the span between Earth and the Sun down dozens or even hundreds of times and still have room to spare. Astronomers have given them a compact name, Jupiter, mass, binary objects, but the nickname hides their strangeness. Planets are usually born in the glow of a young star, pieced together grain by grain from dusty disks, their identities shaped by the warmth and gravity of a parent sun. To find pairs adrift, unmoored, suggests a different upbringing or a gentle kind of exile. The mind reaches for ways such pairings might form. In one picture, these worlds began in a star's disk, like their more domestic cousins, then were nudged and jostled during the restless adolescence of a forming system. A close pass with a massive neighbor, a resonance that amplified over time, a chain of pushes and pulls, and the smallest bodies were flung outward into darkness. Two objects that happened to be near each other in the final seconds of their departure could remain loosely bound, 1,000 million-kilometer partners sharing the same corridor through space. In another picture, clumps in a dense, collapsing cloud, cooled enough to become giant planets directly, side by side, never attached to a star at all. Either way, the pairs speak of gravity's thrift. Once it has tied a knot, it holds on. The surprise deepens when radio telescopes turn their dishes toward these dim couples and find not silence, but flickers of high-frequency sound, not audible, of course, but songs in radio light far above the comforting murmur we're used to from planetary auroras. The emissions arrive in different personalities. Some are steady, as if a lighthouse were sweeping a calm bay. Others come as sudden bursts, irregular and bright, like summer lightning at the horizon. At gigahertz pitches, these signals live in a register we more often associate with compact cosmic engines or with the signatures of technology. Hearing them from cold, starlightless worlds invites a careful curiosity rather than alarm. It helps to imagine each pair as a dynamo. Two massive bodies circle a shared center, tides rising and falling inside their interiors with every pass. Motion through a thin haze of charged particles, leftovers from the nebula's glow, twists magnetic fields into braids. Differences in rotation, differences in conductivity, differences in the pace of their dance turn these braids into power lines. Current flows along the magnetic rails and lights up the radio sky the way an aurora lights up a polar night, only at pitches and intensities we had not expected for planets. If the spacing between the partners changes, the rhythm changes. If the tilt of a magnetic axis shifts, the melody shifts too. No pair needs to sing the same way as another. Each becomes its own small weather system in a universe of bespoke weather. The thought that so many couples fill just one nursery carries a gentle implication across the Milky Way. If orphaned pairs are common in Orion, then other star-forming regions, Carina, Perseus, Cygnus, may host their own swarms, faint and slow and numerous. The galaxy could be veined with uncounted worlds moving through night without a dawn. There is a melancholy in the word orphan, yet these bodies are not bereft so much as differently at home. They keep their heat in the old ways, leftover warmth from formation, a measured trickle from radioactive elements in their cores, and the tides tugged up by a companion's gravity. In the deep cold, even small fires matter. Their skies are black, their stars unmoving, but the bond between twins provides a clock, a pulse to measure the centuries. Listening to these couples changes how we picture the evolution of planetary systems. Not every disk story ends with a tidy set of orbits around a central sun. Some stories spill into the outskirts, where gravitational encounters sculpt new arrangements. That does not diminish the grace of the process, it widens it. Diversity in outcomes means more laboratories for physics, more ways matter can gather, more paths for chemistry to walk. The Orion pairs make a soft promise. The galaxy is more varied and inventive than any single model has room for. The variety extends inward, to places where stars are young and their disks still wide, but the chemistry behaves like a plot twist whispered near midnight. In a bright pocket of the sky, known to catalogs as NGC 6357, a newborn system carries a disk that looks, by mass and shape, ready to build rocky worlds. The region close to the star where a planet like Earth might one day settle should gleam with the spectral signature of water vapor, that familiar pattern of lines we've learned to read in countless other protoplanetary kitchens. Instead, the rainbow is heavy with carbon dioxide, and water's marks are faint, as if written in disappearing ink. The contrast is startling in the quiet way surprises in science often are. Water is abundant across the cosmos. It freezes onto dust grains in the cold outer disk, rides inward on migrating pebbles, and vaporizes near the warmth of the star, building a reservoir that shapes geology, atmosphere, and, on friendly worlds, cycles of cloud and rain, to find instead a pantry stocked with carbon dioxide suggests a different recipe entirely. Imagine dust grains with skins of CO2 rather than H2O. Imagine inner regions bathed in ultraviolet light so insistent that water splits and its lightest part hydrogen slips away, leaving oxygen to find carbon and settle into a tighter bond. The result is not a failure. It is an alternate menu. A world assembled under such conditions would grow crust and mantle beneath a sky flavored by carbon rather than water. Volcanic gases would carry different proportions. Rocks would weather in unfamiliar ways. The first atmosphere would rise from the surface with an accent we do not hear at home. Whether such a world can support life of any kind is a question too large for a bedtime story, but it is a good question to keep nearby. It reminds us that habitability is not a single mountain peak but a range, and that valleys we once assumed empty may be full of trails. The causes behind the carbon-rich signal can be tested with patient watching. If the star and its neighbors flood the disk with ultraviolet light, then the chemistry of the inner region will continue to favor molecules that hold oxygen tightly and leave little water behind. If, instead, the dust grains formed in an environment where carbon dioxide condensed more readily than water and kept that coat as they drifted inward, then the disk is telling us about its birth cloud and its temperature history. In both cases, small differences in early conditions lead to large differences in outcome. The nursery matters. The neighborhood matters. time and light matter in the slow work of building planets. Diversity in chemistry pairs naturally with diversity in weather, and few places display that drama more tenderly than a small, brutal world locked in a tight embrace with its star. There is a planet in a nearby system that circles so quickly you could count its years in hours. One face lives in constant day, glazed with heat. The other inhabits a night that never ends. The surface runs hot enough to soften most metals. Rocks themselves can join the air, by the quieter rules we first wrote for atmospheres. Such a world should have been scoured clean long ago by the stars' wind and glare. Measurements taken in the mid-infrared tell a different story. The day side is not as hot as bare rock would be, and the night side is not as cold. Heat is being moved from one hemisphere to the other with a surprising efficiency, as if a great invisible river is flowing over the terminator and back again. That river can only be air, and the ingredients it carries are not the familiar mix you'd breathe on a temperate shore. Spectra point to carbon monoxide and carbon dioxide as sturdy participants in this steam and stone weather, gases that can survive at temperatures where water splits and simpler molecules flee. The likely source is not leftover primordial gas from the system's birth, which would have been stripped away in the first bright fury. The source rises instead from the crust and mantle themselves. Tidal stresses from the close star knead the planet like dough. Internal heat blooms, fractures open. Volatile-bearing minerals give up their cargo to the sky. Outgassing builds the blanket, even as starlight tears it, and the cycle repeats. Material evaporates on the day side, races upward and around on screaming winds, cools into liquid or solid on the night side, falls as unfamiliar rain, and creeps back toward warmth to begin again. Geology and meteorology become the same subject, written in two scripts on a single page. Weather there would be a choreography beyond anything we can stage on Earth. Jet streams may reach thousands of miles per hour. Clouds, if that is the right word for suspensions of rock vapor, might hang in arches near the boundary between day and night, their particles shimmering as they condense and re-evaporate. A mineral monsoon pulsing with the planet's rotation. Lightning, if it forms at all in such a furnace, would be a chemistry lesson made visible, exchanging charges among ash and vapor and dust. None of this is cruelty. It is simply a different equilibrium, the way a candle flame is an equilibrium between wax, heat, and air. The existence of a thick, working atmosphere in such a place tells us that gases can endure under conditions we once wrote off as impossible. That does not mean every close-in world will carry air. It means we must widen the map of where air is allowed. When we look at other systems and sort planets by their distance from a star, temperature is a good first guide, but not a final truth. Internal activity, tidal forcing, and the chemistry of crust and mantle can tip the scales. A world too hot for water may still move heat and shade its surface with a veil of carbon-bearing gases. A world too cold for comfort may still wear a sky built from freeze-thaw cycles and slow eruptions. Variety keeps our curiosity nimble. Returning to the Orion pairs for a moment, consider how these themes interlace. Worlds cast out from their birthplaces carry their chemistry with them into the dark. If they travel as couples, their tides knead out heat that makes a difference. You can feel only in arithmetic, but that arithmetic matters over millions of years. If they sing on radio frequencies, that song is a message about magnetic fields and rotation and charge, a way to read their interiors from across light years. Meanwhile, in bright nurseries elsewhere, disks that look ordinary by mass and size tell us, by the light they emit, that the shelves are stocked differently. The same physics, expressed under different conditions, yields distinct stories. It is tempting, in the presence of so much variety, to seek a single unifying thread that ties every example into a neat bow. The universe seems to prefer braids. Gravity, radiation, chemistry, and time weave through each other to make the tapestries we observe. Where gravity leads, matter follows. Where light carves, molecules reorganize. Where tides persist, heat accumulates. Where heat flows, weather wakes. In that weaving, planets can become orphans and still find companionship. Disks can build rocks without much water, and a world of fire can keep a sky by breathing from within. Nothing is broken. The loom simply has more shuttles than we first counted. All of this falls softly into the larger lesson Webb has been teaching since its first images. The universe is generous with pathways. Stars are not the only lanterns in the early dark. Black holes can be beacons too. Galaxies do not all grow by mergers alone. Some are helped by direct collapses lit by streams. Planets do not all conform to the rules we wrote from a single sample of 8. Some travel in pairs without a sun. Some begin life in kitchens where carbon dioxide, not water, is the flour on the counter. Some cling to the edge of a furnace and still find a way to cycle air from day to night and back again. Let those pictures settle as you breathe. Picture 2 faint globes sweeping around a shared center, their invisible wires of magnetism humming. Picture a young star's disk, inner regions drawn in crisp lines by carbon's bonds, water's handwriting barely visible at the margins. Picture a small, blazing world, wrapped in a river of air it pours from its own crust, heat sliding around the terminator like silk on a wrist, vaporized rock drifting and condensing in a ceaseless mineral rain. There is nothing to fear here. There is only the steady widening of our sense of what worlds can be. Somewhere in Orion, a pear completes another slow turn. Somewhere near a star in the scorpion's tail, dust grains trade coats in ultraviolet light. Somewhere close enough to name and study again next year, a hot planet exhales and inhales its atmosphere in a loop that glows in infrared eyes. The night holds all of this at once, unhurried. As you rest, the instruments keep listening, the spectra keep unfolding, and the cosmos continues its quiet habit of offering new ways to understand it. One whispering signal, one altered rainbow, one unexpected breeze at a time. The furnace world's breathing sky fades into the background, and another traveler slips into view, small, dark, and older than any story we tell about home. It is a comet, no brighter than a smudge through most telescopes, 7 miles of rock and ice wrapped in a fragile halo. From a distance it looks ordinary, yet its age reaches back beyond the birth of the Sunday. Webb's finely tuned eyes read the glow around it the way a botanist reads rings in a tree, and the signature is startlingly ancient. This visitor has wandered for roughly 7 billion years older than Earth, older than Jupiter, older than the heat that first lit our sky. Tracing its path is like following a crease in the galaxy's fabric. The comet approaches on a steep, almost ruler-straight trajectory that doesn't care much for the sun's politics. It obeys the broader gravity of the Milky Way, skimming our neighborhood as if we were a hill on a larger map. Its speed is fierce, fast enough to cross a continent in the time it takes to draw a breath, and its chemistry is a quiet clue to its birthplace. Where comets, raised in our backyard, typically exhale water vapor when warmed, this one sighs carbon dioxide. The spectrum Webb records is heavy with CO2, a sign that the nursery where it formed followed different recipes than the cloud that birthed our system. That detail is less a shock than a gift. It tells us that long before our sun burned, some other star kindled, lived, and died, leaving behind fragments of its kitchen. Perhaps a stellar death flung this comet out, perhaps slower reshufflings in a distant system sent it wandering. For billions of years, it drifted in the cool between stars, a sealed jar of chemistry from a time when heavy elements were rarer and star formation ran hotter and faster. Now, by simple chance and the geometry of orbits, it crosses our field of view. We watch, we collect its light, and we learn. The thought widens and becomes gently humbling. If we have found one such traveler, then statistics whisper that there are more, perhaps many comets and fragments from other suns passing quietly through the outskirts of our system, too faint to notice unless we are looking in exactly the right way. Each would be a different time capsule, carrying the flavor of a lost neighborhood, a lost star. And the comet offers, without malice, a reflection of our own future. When our sun swells and changes in a few billion years, when gravitational tides and stellar winds rearrange the orbits of whatever remains, pieces of us may be flung outward as well, pebbles of Earth's cousins, husks of long, quiet comets, drifting into someone else's sky as ancient messengers. The scale of that timeline is soothing if you let it be. Against those eons, our questions slow down, and patience becomes the natural unit of thought. We follow the interstellar comet's arc, listen to its carbon-rich breath, and file it among the growing set of hints that the galaxy is a museum without walls. Then, without raising our voice, we turn our gaze outward again to a deeper darkness where the first billion years still shimmer in Webb's images, and there we find a different sort of puzzle. Tiny red glows scattered like embers on black velvet. At first glance, they look simple pinpricks leaning toward crimson, the usual sign of great distance, but they shine with an intensity that refuses to stay tucked inside our current categories. Each is brighter than a small galaxy ought to be. If built by the slow arithmetic of early star formation, they are neither obviously extended like star cities, nor comfortably point-like like solitary beacons. Some flicker and flare in energy bands that hint at furious processes. Some spread their light just enough to make us wonder if we are seeing dense knots of stars igniting all at once. They have been gathered into a shy census, hundreds catalogued so far, and the more we count, the less they resemble any tidy population we've met. Color, in astronomy, is time's accent. Red can mean distance, but it can also reflect dust, temperature, and the stretching of light by the universe's expansion. These objects live at distances where the first structures were just learning their steps, and yet they sing loudly. Spectral energy distributions, those carefully modeled curves that parcel light by wavelength, say their engines are powerful and compact. Some emit high-energy whispers, X-rays, and ultraviolet hints that sound like matter falling toward deep gravitational wells. Others glow in patterns that echo starbursts, clouds collapsing quickly, a crush of newborn suns turning gas into radiation at a rate that outruns our expectations. It is as if the early universe opened more doors than we realized, letting multiple kinds of brilliance share the same stage. One way to hold this without gripping too hard is to imagine a spectrum not just of light, but of possibilities. At one end, some of the little red dots could be small galaxies whose star formation was turbocharged by their environment, dense filaments feeding them, dark matter halos deeper than average, cooling pathways that allowed gas to condense without stalling. At the other end, some could be compact accreting black holes, black holes wearing bright masks of starlight and hot gas whose feeding made them look, from afar, like undersized galaxies with oversized hearts. Between those ends, there may be hybrid scenes, where a central engine and a starburst grow together, each fueling the other. The distribution of these dots is as telling as their brightness. They do not huddle only in the densest nodes of the early cosmic web. They appear across the fields, as if the first billion years offered frequent opportunities for rapid assembly wherever conditions quietly aligned. The cosmos, then, was denser, gas was more pristine, interactions more common. In such a setting, thresholds are easier to cross. A slight excess in inflowing material, a cooler pocket, a steadier stream along a filament, and a region could surge past the usual pacing, making stars or feeding a core with unusual vigor. The result, seen from the great later distance we occupy, is a sprinkled pattern of red lanterns outshining their size. What makes the puzzle kind, rather than cruel, is that every outcome teaches. If a portion of the little red dots are compact black hole engines, then we have further evidence that seeds, whether primordial, direct collapse, or both, were plentiful, and that early feeding was efficient. If another portion are extreme star-forming clumps, then our recipes for cooling, fragmentation, and feedback in the infant universe need more spice. Either way, we refine the models, not to tame reality, but to let our equations admit more of it. You can picture the work as a gentle unbraiding of light. Infrared images give us the positions and the first hints. Follow-up spectra mark the distances more precisely and sketch the chemistry in broad strokes. Variability studies, quiet patience over months and years, reveal whether a source flickers like a compact engine or glows steadily like clustered stars. X-ray and radio observations add other flavors to the profile, tracing the hottest gas and the most ordered magnetic fields. No single instrument draws the portrait. The portrait emerges like a face appearing in low light as your eyes adjust. There's also a philosophical ease in meeting objects that do not fit, especially at the edge where time was young. The early universe did not read our textbooks before it acted. It followed the pressures and flows available to it, shaping matter into temporary balances that made light. Our task is to be good listeners. The small red points, whether they are baby galaxies burning the candle at both ends or compact beacons feeding in dusty cradles, are messages about conditions we cannot recreate. Their energy is not a threat, it is a record. Hold the comet and the red dots together in your mind for a moment. One is a single relic wandering into our yard, carrying the memory of a system long gone. The others are a crowd of distant lights from a shared epoch, each telling us that the universe, even as a child, already knew several ways to shine. Both speak across gulfs of time with the same language, spectra and brightness, motion and color. Both invite patience and a soft grip. As the night deepens, let those invitations settle into the rhythm of your breathing. Somewhere above the ecliptic, a streak no wider than a thought glides past the sun and returns to its long, dark road, leaving us a trace of carbon to puzzle over. Far beyond any comet's leash, in the first billion years where structure was still inventing itself, small crimson embers persist in Webb's vision. Neither galaxies as we've known them, nor engines as we've neatly categorized them, but something in between or beyond. Nothing here demands alarm. The cosmos is simply reminding us that variety is its native tongue, and that understanding grows best when we listen quietly for what we did not expect to hear. The trail of tiny crimson embers fades to the edges of vision, and the canvas widens until patterns begin to breathe across impossible distances. In that wider view, Galaxies are not only islands of stars, but also arrows, each disk a faint compass, each spiral a gesture. When astronomers let Webb's deep survey add its quiet layers of detail and then listened for orientation, a subtle rhythm emerged. Across stretches of space so vast that a beam of light would need millions of years to cross them, many galaxies seem to turn in the same general way, as if distant windmills were catching a breeze no map can show. It is not a perfect chorus. Nature rarely sings that way, but it is coordinated enough to make patient minds sit up in the dark. Under the simplest stories, structure forms without memory of a preferred direction. Early ripples in matter amplify, filaments grow, galaxies spin up from the angular momentum of local flows, and distant regions remain strangers to one another. A shared spin across such gulfs hints either that the universe carried a faint twist from its birth, or that some gentle hand, an unseen field, a large-scale pattern in initial conditions, nudged separate neighborhoods into a family resemblance. Neither option is a demand. Both are invitations to think more broadly. If the beginning contained even a whisper of rotation, that whisper could thread through later growth the way a grain runs through wood. Subtle, persistent, setting a texture that emerges only when you stand back. If instead there is no primordial spin, then the alignment suggests physics that can communicate preference across scales we had assumed were safe from conversation. This kind of clue does not overturn a cosmos in an instant. It asks us to soften the edges of our models. A preferred direction on the largest scales could gently bias how matter settles, how jets from black holes thread their way through galaxy halos, how cosmic voids stretch and relax. It need not be loud to matter. Even a slight anisotropy, unevenness, changes the arithmetic of expansion by a breath, and such a breath, summed over billions of years and billions of light years, might echo in the small disagreements we measure when we try to take the universe's pulse. The idea is not a verdict. It is a working theory set carefully on the desk to be weighed alongside others. There is a philosophical sweetness in this, too. If space-time itself carries a faint directionality, then up and down, left and right, gain quiet cosmological cousins and almost imperceptible along the grain. We would live within that texture, the way a drop of water lives within a current, not trapped, not pushed, simply part of a larger flow that only reveals itself when traced from afar. And if the texture is a projection of something even larger, a parent structure in which our universe is a room among many, then the thought expands without hurry. We need not decide tonight. The stars will keep their counsel while the data accumulates, and the slow pleasure of checking will carry us forward. As the mind drifts along these big patterns, the view narrows again, this time not to a single star or planet, but to a meeting between two great cities of stars. Their disks are gliding through each other in a stately cross, and between their bright cores lies a bridge, a river of gas glowing softly, where tides have stretched and stripped it from each side. The figure they trace is a quiet 8, two loops touching. In the overlap, where theory expects turbulence but no permanent anchor, Webb and its partners have found a deepening well, a black hole gathering itself from the flow, not as a remnant of dead stars, but as the direct consequence of gravity folding a massive gas stream inward. Direct collapse is an old idea sung in a new register by this scene. If gas can reach high densities while shedding heat and avoiding the fragmentation that would seed many small stars, the entire parcel can plunge together. Cooling pathways matter, the presence of heavy elements matters, the tempo of inflow matters. In this collision, conditions appear to have conspired in just the right way. The central engines that each galaxy brought to the encounter are still embedded in their original homes, following the familiar script of convergence. But the bridge between them, enriched, shocked, and channeled, has become its own cradle. Radio eyes mark a compact source, exactly where the dynamics say collapse should focus. Infrared spectra trace heated gas, feeding inward. The geometry of the ringed figure sketches the flow lines like fingerprints in frost. Watching such a cradle at work dissolves some of the unease around the earliest heavy black holes. If the young universe offered many moments like this, streams converging in the nodes of the web, dense pockets cooled just enough to slip past fragmentation, then heavy seeds would be expected, not exceptional. Give a seed a few 100 million years of steady inflow, and you have the bright cores we now see glimmering in dawn's light. Quasars awake early, centerpieces that seem oversized only when we imagine a single, slow path to their mass. With direct collapse, the path begins farther along. The head start is the point. The grace of the figure-8 encounter is that it folds multiple scales of story together. On the one hand, it is the local, specific choreography of two galaxies, trading gas, torque, and time. On the other, it is a small echo of the larger thought about preference. Streams do not meet by accident. The cosmic web channels them, and that web inherits its layout from the first ripples in the hot beginning. If those ripples carried any faint twist or bias, the traffic patterns of gas would reflect it here and there, nudging which bridges become stable, which pockets avoid fragmentation, which direct collapses are favored. Nothing is predetermined, but not everything is equally likely. The universe offers its menu. Gravity chooses with a taste shaped by initial conditions and the chemistry of the moment. The sight of a black hole forming in midstream also recasts the role such objects play. Instead of being only the end products of stellar lives or the punctuation marks of mergers, supermassive black holes become early organizers, anchors that gather gas, seed feedback, and help set the tempo at which galaxies grow. Feedback, that gentle euphemism for energy routed back into the environment, can heat or stir the surrounding medium, preventing runaway collapse in some directions while clearing channels in others. In this way, a central engine can shepherd its environment without dictating it, a lighthouse that also shapes the cliffs. None of this asks you to hold violence in your mind. Even the word collapse, so dramatic on a human scale, is measured and clean at these distances. Gas flows inward, radiates, settles. Stars are born where densities and temperatures invite them. Elsewhere, heat and turbulence wait for the next quiet. Catastrophe in space is choreography in slow time. What looks like an instant in the documents of cosmology is still millions of years, long enough for a melody to play out, long enough for calm to return between phrases. If the early universe was rich in such phrases, direct collapses in bridges, quick alignments of spin along filaments, compact engines lighting up before cities of stars fully formed, then our present variety is easier to understand. The cosmos had several ways to start its structures, and it used them. The aligned rotations seen across distant patches need not declare a single rotating beginning. They can also be the residue of flows that shared a gentle bias and left their mark on how disks settled. The heavy black holes, seen surprisingly soon after the first light, do not have to be miracles. They can be expected guests who arrived by a faster road. Let the two images rest together, the grand, almost whispered rhythm of spins lining up over gulfs of distance, and the intimate brightness of a newborn black hole cupped in a river between two galaxies. One is the suggestion of a grain running through the wood of space-time. The other is gravity, taking advantage of a moment to make an anchor. Both are quiet acts, and both leave trails we can follow with spectra, with radio maps, with the slow art of patient monitoring. We do not need to choose a single story tonight. We only need to breathe, to keep listening, and to let the universe show us how many kinds of order can emerge when time and matter are given room. The idea of a faint grain running through space is easy to carry if you imagine it as texture rather than command a barely there preference that, under patient inspection, shows up in how many distant disks lean the same way. Galaxies separated by gulfs that no practical signal could cross still share a tendency, as if the earliest flows set a rhythm that lingered. It doesn't have to mean the whole of reality is turning like a wheel. A whisper would do. A slight bias in the first swirls of matter, a filamentary web spun with a gentle twist, would leave signatures that later structures inherit. From our vantage, those signatures appear as families of spin, faintly coordinated across the dark. Hold that softly, and the questions open in a calm arc. If there is a preferred direction, even a modest one, then some laws we treat as perfectly symmetric may, on the largest canvases, carry a subtle accent. Expansion could be almost, but not perfectly, the same in every direction. Feedback from active galactic nuclei could couple to the surrounding medium in ways that are easier along the grain and a touch harder across it. Jets might tend to thread halos with a common handness more often than chance permits. The differences would be small, yet small differences in a universe given billions of years can grow into the quiet anomalies we keep noticing when we compare one cosmic yardstick to another. None of this insists. It proposes and then waits for better data. There is another sense in which a preferred direction is comforting rather than alarming. It anchors our maps without centering us. We are not in a privileged place. We are in a textured field. Whether that texture reflects a deeper parent structure in which our patch of space-time is a room within a larger house, or simply the imprint of initial conditions we do not yet know how to derive from first principles, the practical work is the same. Trace it, test it, and see whether it coaxes stubborn puzzles into alignment. The pleasure resides in the method: more measurements, cleaner statistics, the follow-up with instruments that hear different notes until what was suggestion becomes chorus. From these long, slow questions, the view narrows again to a meeting written in clearer lines. Two disk galaxies pass through each other like dancers in intersecting arcs. Where their paths cross, tides draw out luminous streams. Gas, shocked and cooled, pools in a bridge that glows. At the midpoint, gravity is busy with an unusual task. Instead of passively ferrying material from one nucleus to the other, the bridge is becoming an anchor of its own. The light there bears the signature of matter falling toward a compact center, and radio maps sharpen that signature into a point. What is assembling is a black hole, not as an afterthought of stellar deaths, but as the direct consequence of a massive gas flow losing pressure support and slipping past fragmentation. The steps of that dance are quiet to describe and extraordinary to watch. For gas to collapse directly, it must shed heat efficiently enough to keep falling, and it must avoid breaking into smaller pieces that would become stars. Metallicity, the abundance of heavy elements, matters because it changes how the gas cools. Radiation from nearby sources matters because it can dissociate molecules that would otherwise encourage clumping. The rate of inflow matters because a steady river builds depth in the center. In the figure-8 encounter, these requirements appear to be met in the bridge. and the result is a deepening well, exactly where simple expectation prefers none. Seeing that process at work turns a set of early universe surprises from paradox into path. If some regions could form heavy seeds by direct collapse, then the bright cores we see very soon after the first light did not all have to climb the same long ladder. They could begin on a higher rung and proceed at a pace that matches what we observe. It also invites a reframe of causality. Rather than treating supermassive black holes only as byproducts of assembled galaxies, we can let them be co-authors from the beginning objects whose early emergence guides the later flow, moderating star formation here, stirring gas there, shaping the thermodynamics of their neighborhoods in ways that propagate outward over time. The scene also suggests a universe that found several quick routes to complexity and used them as needed. In some places, stars led and central engines followed. In others, engines arrived early and helped the stars along. Elsewhere, both grew together in feedback loops, outflows, carving cavities that later fed inflows, bursts of star formation, enriching gas that later cooled more efficiently. The picture is less a single rule and more a grammar. Gravity, cooling, inflow, feedback, and time composing sentences in different orders to say galaxy in many dialects. Return, just for a breath, to the hint of large-scale preference. Streams do not meet at random. The cosmic web guides them along filaments into nodes, and if those filaments were laid down with even a slight handedness, the places where bridges form would inherit that bias. Over many encounters, that could imprint a statistical spin on the disks that grow from those flows, not as a destiny for each galaxy, but as a tendency for many. In that way, the largest suggestion and the most intimate laboratory, an aligned set of rotations, and a newborn black hole in a bridge start to feel like verses of the same song, each giving the other context. The word violence sometimes creeps into these stories, but the closer we listen, the less helpful it becomes. Collisions in space feel sudden only because our language is sized for afternoons and seasons. At cosmic tempos, even a collapse is a measured surrender of pressure to gravity, a steady conversion of potential into light. The spectacle we imagine from a single image resolves, under long watching, into a choreography of flows that begin, pause, and resume. Catastrophe, scaled up and slowed down, becomes process. What makes this soothing rather than merely technical is the way it simplifies our own task. We do not have to solve the universe tonight. We let Webb and its companions collect the data that turns suggestions into tests. We compare the orientations of hundreds of disks and ask whether their lean exceeds what randomness permits. We map bridges between merging galaxies and watch for compact sources that grow over months and years. We fold in X-rays where hot gas speaks, radio light where magnetic fields and jets draw their lines, and infrared where dust and molecules carry the plot. Each wavelength adds a stanza. The poem is written by the sky. We simply keep reading. Part of that poem's comfort is the reassurance that impossible is often our word for not yet modeled with enough breadth. Coordinated spins across great distances do not have to signal a breach of symmetry. They can be the long echo of initial conditions we're only now learning to measure. A black hole forming between two galactic cores does not need to break stellar evolution. It can bypass it when the ingredients and the kitchen allow. Every time we broaden the recipe book, primordial seeding here, direct collapse there, rapid feeding where flows converge, the earlier alarms quiet, and the pattern comes into focus. Let the images blend as you rest, spirals far apart, gently agreeing on which way to turn, a narrow bridge between luminous cores, brightening at the midpoint as if a new lantern had been hung. Gas moving with patient purpose, cooling, sinking, warming, shining. The universe is not hurried. It lays down texture at the beginning and lets time reveal it. It arranges streams so that anchors can arise when needed. We meet these arrangements without urgency, tracing them at the pace of our breathing, grateful that a mirror in deep space can show us how order grows from a handful of elements and a long night. Far out in the deep, a face seems to look back, two luminous ovals for eyes, a pale sweep of feathers traced in dust and gas. Astronomers nicknamed it the cosmic owl, a tender joke to make the unfamiliar feel close. Under Webb's softer, longer wavelength gaze, the whimsy gives way to weather. Those feathers are not ornaments, they are streams, long, trailing filaments of stars and gas, pulled from the galaxy's body, like silk teased by wind. In clusters, the space between galaxies is not empty. It is a hot, thin sea. When a galaxy swims through that sea, the headwind presses on its gas, the way air pushes on a scarf from a car window. This is ram pressure stripping, and once you see it, the owl's posture makes sense. The core bright, the outskirts combed backward into tentacles hundreds of thousands of light years long. Tentacles sound dramatic, but the process is gentle in its own scale. Steady pressure, steady loss. The gas most loosely held is peeled away first, then denser strands follow. Along these luminous wakes, something unexpected blooms. Compression is a quiet midwife. As the stripped gas piles and cools, knots collapse, and newborn stars flare blue against the dark. A galaxy can lose and make at once, shedding its outskirts while seeding lonely nurseries far from home. The cosmic owl becomes a paradox in motion, being unstitched while embroidering the night with new clusters that will, over eons, drift and thin into the general light. Once you've learned to read this signature, you begin to see it everywhere. Jellyfish, galaxies, disks with streaming tails pepper deep fields and cluster rims. They hint that galaxies do not glide serenely through a placid void. They shoulder their way through tides and crosswinds. They exchange matter with their surroundings. They suffer and flourish by turns. The cosmic web's great filaments, which shepherd galaxies toward one another, are not just scaffolds for gravity. They are environments with texture and temperature, places where ram pressure, shocks, and turbulence reshape what a galaxy can be. The owl is a single stanza in a long poem of drift and weather. Inside those tentacles, the stars are refugees only in metaphor. They are simply farther from a galactic nucleus than most, and their orbits now belong to the cluster's wide geometry. Some will be captured by neighbors, some will wander the intra-cluster medium as part of a ghostly, low-surface brightness glow that sketches the cluster's history in faint strokes. Here and there, heavy elements born in brief lives, oxygen, carbon, nitrogen, begin their patient journey outward, where later clouds might use them to build rocks, atmospheres, and, in lucky places, chemistry that learns to learn. It is easy to call this violence. It is more accurate to call it weather stretched over millions of years, with cloudbursts and long calms, with losses made visible and quiet gains left to accumulate in the dark. Chemistry, too, carries a surprise in this early era. We are used to the idea that heavy elements, anything beyond hydrogen and helium, arrive slowly, forged in the cores of massive stars, and given back to space by supernovae. That process is a relay. The first generation of stars, astronomers call them population 3, are almost pure hydrogen and helium. They flare hot and large, live brief lives, die spectacularly, enrich their surroundings, and then the second generation forms with a trace of metals, and the third with more, and so on, each cycle steeping the medium in complexity. On this cycle, our expectations rest. Metallicity rises over time. The early universe should be simple. Webb spectra loosen that certainty. Young systems, galaxies seen when the universe was less than 1 billion years old, show the fingerprints of oxygen, carbon, and nitrogen in proportions that feel too mature for their age. In the most striking cases, bright hydrogen lines glow alongside features that imply significant enrichment only a few 100 million years after the first dawn. One small galaxy, seen a mere 330 million years after the beginning, wears such signatures openly, as if generations had already passed. There are ways to make sense of this without throwing out the script. If the earliest stars were very massive, hundreds of times the sun's mass, then their lifetimes would be measured in a handful of million years, not tens. They would pour out radiation, seed their neighborhoods with ions, explode with hyperenergetic force, and chase their elements far and wide. A couple of such generations could, in short order, raise the metallicity enough to produce the lines we see. Another path is less specific and more philosophical. Perhaps our models have been too tidy about mixing. Feedback, turbulence, outflows, and inflows may have stirred metals efficiently into certain pockets while leaving others pristine, creating a patchwork where some regions evolve chemically much faster than the global average. In a clumpy, filament-fed universe, early and late can be neighbors. A few voices also entertain the possibility that unknown processes added to the ledger, exotic transients, early shocks, or physics that imitates enrichment by altering the way we read the lines. These are working theories, set gently on the table with the same rule as always: make predictions, invite refutation, keep the tone calm. What matters for our drift through the night is the feeling that complexity did not hesitate. Where gas gathered and cooled, stars rose and fell, quickly enough to write chemistry into the margins, well before our simplified pictures expected it. If metals came early in some neighborhoods, then the ingredients for rocky worlds, atmospheres, and complex molecules might have been ready early too. That does not mean life was abundant. It means the pantry was stocked sooner in places with the right temperatures and the right chance alignments. You can let the idea pass like a breeze. Somewhere, long ago, pebbles clicked together in the dark. Somewhere else, steam and stone made temporary skies. In a few pockets, cycles started that might, given time, have learned to store information in molecules. The universe has had plenty of time to practice while we sleep. Closer to home, a different kind of riddle peeks across the fence, then ducks away. In the glow around our nearest sun-like neighbor, a warm signature flickered a point whose color and brightness matched what we'd expect from a Neptune-sized world, circling at a distance that keeps surfaces temperate. The thrill is obvious. A nearby planet, perhaps with mild seasons, perhaps with clouds, in the next stellar system over. Follow-up observations are how we turn hope into knowledge. When the instruments looked again, the signature was gone. It is tempting to tell a dramatic story. The less romantic version is also the more interesting one. Infrared brightness can vary for reasons that do not require a planet to vanish. dust can thicken and thin along our line of sight. In a system where old collisions are grinding rocks to powder, a nascent world can feed in bursts from a leftover disk and then go dark. An orbit can be eccentric enough that thermal emission swells near close approach and slips below our thresholds the rest of the time. In a binary system like Alpha Centauri, dynamics are intricate. Stability and illumination change across a maze of resonances. It is also possible that the original signal came from a different kind of source, a warm clump in a debris field, a transient glow from gas briefly heated and then cooled. None of these ideas are failures. They are hypotheses, being trained by data. What matters is not the outcome of a single candidate, but the way the search teaches us to read. The nearest bright stars are complicated, lively places. The instruments that can disentangle their subtleties are learning to do so by repetition. Watch, model, return, compare wavelengths, track seasonal variation. Let the system tell you its tempo. A planet that comes and goes in our measurements is not mischief. It is a system saying, look closer, in a language of light and time. Under and around all of this, threads we cannot see directly braid the large-scale structure, and Webb's portraits hint at their presence in a new register. Magnetic fields, everywhere they exist, are gentle organizers. They guide charged particles, shape the flow of gas, and store energy that can be released in sudden reconnection events. Magnetic knots, untying themselves and warming their surroundings. We are used to thinking of such fields as local phenomena around stars, in disks, near jets. The surprises in deep images and clever analyses are twofold. First, that fields seem to trace the filaments of the cosmic web itself across enormous distances. Second, that their patterns show a richness more like a network than a simple, uniform thread. Scientists reach for the same mathematics they use to understand connectivity in other complex systems. Nodes and links, clusters and paths, degrees of centrality. These abstractions are indifferent to domain. Apply them to filaments, lit by faint emissions, and you can test whether the connections are random or structured, whether certain junctions act like hubs, whether paths prefer some routes over others. The early results suggest that magnetism was not an afterthought painted on by later generations of stars. Fields may have been seeded early and then folded, stretched, and amplified by the same flows that sculpted matter into filaments and sheets. In that sense, magnetism is not separate from gravity's architecture. It is part of the blueprint, influencing how gas cools, where it lingers, and when it collapses. If reconnection events and magnetic pressure modulated the first star formation, then stellar masses, cluster sizes, and even the timing of chemical enrichment could differ subtly from what a gravity-only picture would predict. The effect need not be large to be meaningful. A small resistance here, a brief encouragement there, and the path of cooling gas changes by just enough to tip a region toward or away from a burst of stars. Add those small tilts across many nodes, and the early universe's timetable adjusts faster in some lanes, slower in others, until what we observe as unexpected metallicity or hyper-efficient starbursts becomes less mysterious. Comparisons to the brain are poetic and therefore easy to overread. Neurons exchange signals, filaments exchange matter and momentum. One learns, the other obeys physics. Still, the mathematics that reveals hierarchy and modularity can be fairly applied to both, and the visual echo is striking. The point is not to claim sentience for space. It is to admit that complexity emerges wherever many simple interactions are allowed to run for a long time under gentle constraints. A magnetic network that forms, breaks, and reforms across eons is not alive, but it is lively. It responds, stores, and releases. It channels and redirects. It leaves scars and signatures in the places where gravity's river meets magnetism's banks. That liveliness circles back to earlier puzzles with a satisfying economy. If the filaments that fed early galaxies were magnetized in intricate ways, then some bridges and mergers would have been better at keeping gas cold and cohesive, ideal for direct collapse, while others would have been shredded into star-forming tatters. If large-scale flows carried a faint bias and twist, then disks settling from those flows would inherit it, producing the mild, statistical alignments we now suspect across wide fields. If magnetic pressure occasionally thickened a region just enough to delay fragmentation, then supermassive seeds would have an easier time forming. The universe is parsimonious, a few tools used many ways. Let the images stack softly in your mind. The cosmic owl, long strands combed back, blue nurseries glinting where pressure and cooling found their balance. Small galaxies wearing grown-up chemistry earlier than our tidy timelines predicted, as if the forge ran hot in certain corners. A nearby star's glow that held, for a night, the warmth of a world and then exhaled it back into ambiguity, an invitation to watch more carefully. Map thin threads stretching between clusters, humming with fields that coax gas to flow this way instead of that, storing energy that will be given back in a crackle of heat somewhere down the line. None of this demands fear. It asks for attention, the unhurried kind. Webb's talent is not only the depth of its images, but the patience it inspires. Follow the tentacles, read the rainbows, compare the flickers, trace the hidden wires. With each step, the cosmos feels less like a place that breaks rules and more like a place that writes more rules than we first realized. Rules that allow weather to strip and knit, chemistry to bloom early, planets to hide in plain sight, and magnetism to sketch a web as intricate as lace across the largest canvases we can see. Breathe with that. The owl keeps swimming, the tentacles keep birthing and thinning. Somewhere a candidate planet waits to be caught again in the act of warming. Across distances, our minds can hold only in metaphor, fields, thread, filaments, and nudge the fate of clouds. Complexity is not an intruder. It is the native dialect of a universe that has had time to practice. And as the night deepens, the instruments keep their quiet vigil, collecting the faint syllables that, strung together, become stories gentle enough to sleep by and sturdy enough to learn from when morning comes. Closer to home, where the Milky Way gathers its spiral arms like a shawl, a deeper darkness waits a quiet well, 4 million suns deep. Sagittarius A times sits there, not as a hole in the sky, but as a place where the sky folds back on itself. In the near infrared, Webb watched patiently, not for minutes, but for nights, spread across a year, letting faint warmth from swirling gas sketch the mood at our galaxy's heart. What emerged was not a metronome, but a restless lantern, a low, simmering glow, broken by sudden flares. Then a return to hush, then another bright thought, as if the center were breathing without a clock. The flicker is not a simple pulse. It meanders, swells, and vanishes again, refusing the tidy comfort of periodicity. Up close, where up close still means light, skimming the edge of the point of no return, plasma moves like weather on a surface that isn't a surface, tangled in magnetic fields that twist and snap and reconnect. In that tangle, energy stored like a wound, spring releases in a moment, lighting the accretion flow the way lightning textures a cloud. This is the small-scale storm: turbulence, compression, a brief surge of heat, then cooling and drift. And then there are the larger flares, flashes that feel like whole parcels of matter crossing a threshold, a place where light can orbit briefly before choosing escape or surrender, and where a tiny change in trajectory decides a great deal. None of this announces new laws so much as it brings us right to the edge of the old ones and asks us to listen. General relativity shapes the stage, space-time curved so hard that orbits warp into spirals and time itself stretches. Electromagnetism and fluid dynamics choreograph the dancers: charged gas, thin but lively, carried by fields that draw loops and braids in 3 dimensions. Somewhere between those descriptions, in layers too thin to see directly, quantum effects begin to matter, not everywhere, not loudly, but in the way fluctuations seed instabilities, or in how energy cascades from large eddies to small. When astronomers say there is no pattern, they do not mean there is no order. They mean the order lives in chaos, the kind that makes weather forecasts murky while climate remains knowable. If you step back from the data and let the metaphor breathe, Sagittarius A times becomes less a monster and more a hearth, variable and alive, adding a moving line to the long poem of our home. Its irregular brightness does not violate information. It reminds us that information rides on light, and light's road near the horizon is crowded and curved. Flares are not destruction. They are the disclosures of a system that stores and releases, in rhythms too rich to be periodic. To watch is to learn the patience of the center. From that intimate jitter, the view widens until whole cities of galaxies share the frame. In clusters, hundreds of star systems move in the gravity of mass we cannot see directly, the way buoyant leaves drift where the river runs strongest beneath the surface. Collisions between these cosmic cities are slow in human terms and furious in physics terms, releasing energies spread across millions of light years. We have long known the obvious firework shocks that heat gas to X-ray brightness, arcs of radiolight where particles are whipped to near light speed, but Webb's sensitivity adds the faintest embroidery: ghostly streams of stars, curving like silk threads between galaxies, ridges and tails, so delicate that earlier eyes passed over them. These streams are the histories of torn things. Tides, raised by deep halos of dark matter, pull at outskirts first, then deeper layers, unbinding stars from the shallow wells of small galaxies and passing them to the cluster's broad embrace. Some bridges connect current partners, others are fossils of past meetings, stretched thin by time until they barely glow. Seen together, they make a lace across the cluster, a map not only of where mass is, but of how it moved. In this pattern lives a quiet correction to our old picture. The scaffold of dark matter is not only a static frame on which baryons, the everyday matter of stars and gas, hang their weight. It is a participatory landscape, shaping not just where galaxies end up, but how they are edited along the way. Whether dark matter does anything beyond gravity, here is a question to hold lightly. Some models allow particles a whisper of interaction that could, under the right conditions, redistribute energy and build or erase substructure. Others keep dark matter perfectly aloof, letting gravity alone compose the music and tidal forces do the shredding. Webb's faint tidal webs do not shout, which is true. They set constraints and force better simulations. The important thing for our midnight drift is the feeling of dynamism on scales we once called serene. Whole galaxies arrive in clusters, not as intact ships, but as fleets already weathered by long seas, shedding plumes that later become the diffuse light between cluster members. Stars born in one city end up lighting another. Gas stripped in one pass rains down as fuel in the next. The Webb is a teacher of patience and recycling. If you carry that lesson forward, the next image is less a surprise and more a deepening of the same theme. In one field, a single massive galaxy bends space so strongly that light from a still more distant system is pulled into multiple routes around it. Each route takes a different time. To us, those routes paint several versions of the same background galaxy on the sky, each version caught at a different moment in its life. It is as if the lensing galaxy had hung mirrors in curved halls and invited history to prance through them, first young, then older, then middle-aged, in an arrangement our eyes render as four bright arcs. Strong lensing is an old prediction in a new key. Einstein's theory tells us mass curves, space-time, and light follows those curves. Astronomers have turned this effect into a measuring tool for decades. What makes some lenses startling is their extremity. Multiple images arrayed with clockwork precision, brightness ratios that only make sense if the lensing galaxy's mass is not smooth but clumpy. Time delays that we can actually time. The delays, measured carefully, become rulers for expansion, cross-checks on the universe's pace. The clumps implied by the brightness patterns become a census of subhalos, small dollops of dark matter that standard models predict in abundance, but that are hard to weigh otherwise. Every wiggle in a lensed arc's light is a fingerprint of mass we cannot see. In this way, a spectacular picture becomes a quiet laboratory. Count the images and you learn the bulk. Measure their separation and you map the shape. Track their flicker and you find the lumps. In the most intense examples, the mass must be distributed in ways that push on our assumptions. More concentrated here, more shredded there. Small companions lurking where no starlight marks them. None of this breaks the theory. It stretches it across a regime where our approximations thin. The geometry is still Einstein's. The materials are still the universe's. The laboratory is simply exquisite. If there is a borderland where quantum gravity might gently edit the classical picture, it will look like this: rare, precise, demanding. For now, the lenses remind us that space can be both smooth and wrinkled, and that time, when bent, lets us watch one thing be many ages at once. Set these three scenes side by side: the jitter at the center, the torn lace of clusters, the mirrored galleries of lensing, and a through line appears. Variability at the heart says the universe is restless even where we imagined quiet. Tidal webs across clusters say structure is continuous, with edges that fray into one another. Lensing says geometry itself participates, turning mass into optics and time into a mosaic. The common mood is not violence, but liveliness, a preference for processes that move energy and information along gentle gradients for very long times. It is easy, in daylight language, to call such scenes disturbing or catastrophic. At night, the words soften. The accretion flow around Sagittarius A times is a pot on low boil, not an explosion. The cluster's stellar streams are driftwood patterns on a vast tide, not wreckage. The lensed galaxy's four faces are a lesson in perspective, not a violation. What changes with Webb's sensitivity is not the universe's temperament but our ability to notice the small, faint streams become visible. Brief flares stand out from the simmer. Tiny mass clumps declare themselves in the way they pinch a ribbon of light. There are, of course, open questions that keep the mind pleasantly awake. Does the center's irregular heartbeat hide any subtle timescales, orbital hints near the photon ring, echo patterns in the cooling tail of a flare, waiting to be teased out with more hours of watching? Do the cluster streams demand a whisper of self-interaction in dark matter, or will gravity alone, plus better initial conditions, recreate their grace? Do the strongest lenses imply more substructure than our models allow? And if so, is that a clue to particle properties or to the messy history of assembly? Each question is a small lamp along a path we already walk. None requires a leap into panic. Even the language of unknown physics can be peaceful when we use it properly. Unknown does not mean unknowable. It means not yet fit to the pattern with confidence. At the event horizon scale, unknown might be the precise way magnetic reconnection cascades energy into electrons in a curved space-time. In clusters, it might be whether dark matter's cross-section is zero or merely tiny. In lenses, it might be how baryons, stars, gas, dust reshape a halo's center and masquerade as exotic mass. These are issues that yield to measurement, to patience, to the slow joy of building instruments that can hold still for a long time. Let your attention sweep through the scenes again, this time as if you were strolling a gallery after hours. First, a panel of the galactic center, shimmering with a granular glow that thickens and thins, threads of hot gas tracing magnetic loops you can't quite see, then a sudden bright knot like a thought arriving. Next, a mural of a cluster, its brightest galaxies crisp and the rest a fog. And in that fog, when your eyes adjust, filaments of starlight tying one island to another, arcs and wisps that speak in a whisper of past tides. Then, an installation of light itself bent into arcs, the same distant galaxy repeated with tiny differences, like portraits painted years apart, this one with sharper features, that one softer, all of them the same sitter seen through time's curve. In each room, the plaque could share the same sentence: patience reveals structure, not because the sky was hiding it mischievously, but because our senses were not yet tuned to its faintness or its pace. Webb's gift is to slow our seeing down, to make the dim substantial and the short-lived legible. Given such gifts, the universe feels less like a code to crack and more like a score to hear, some passages loud, many quiet, all of them layered. The comfort in all this grows if you remember that we are woven into the same fabric. The black holes flicker, and our own heartbeats are separated by scale, not by kind. Both are flows adjusting to constraints. Both are energy moving along permitted channels. The cluster's tidal lace and the rivers that carved long valleys on Earth share the logic of gradients. The lens's time-split faces are cousins to the way a mountain path reveals the same lake from different switchbacks, each view a moment apart. The metaphors do not explain the physics, but they remind us that pattern is a generous thing, repeating its logic across sizes so different that only math keeps the kinship honest. So breathe. At the center, the glow will rise again, then fade, then rise, no schedule, just weather. In the distances beyond, streams will lengthen and thin, new ones will be woven, and clusters will wear their histories a little more plainly for those with eyes tuned to faintness. Somewhere, a lens is already splitting a galaxy into versions of itself we will measure and compare, turning geometry into a clock. None of these require us to hurry. They ask for the kind of attention that fits a quiet room at night, a soft lamp, a mind willing to hold two ideas at once, that the universe keeps laws we know, and that it keeps finding new ways to express them. The gallery grows quieter, and in that hush, another kind of drama comes into focus, smaller in scale than clusters and lenses, closer to the warmth of starlight, but no less transformative. Two stars share a life, circling a common center, and over long seasons one begins to lean on the other. Outer atmospheres brush, a trickle becomes a stream. Gas spills across the space between them and winds into a bright ribbon, a spiral of heat that wraps the hungrier star like a shawl. This is how many binaries age. One partner, usually the heavier, gathers what the other cannot keep. Under Webb's soft infrared gaze, the veil of dust that once hid these exchanges goes transparent, and the choreography appears jets, arcs, and crescents of material flicking away from the donor, settling onto the eater, then flaring as the flow thickens. The earliest stage is almost tender. A puff of atmosphere finds the neighbor's gravity and flows downhill through an invisible saddle between the two stars. The receiving star builds a disk, thin and hot, where friction turns falling motion into light. Small instabilities skitter along the disk's edge like ripples on a pond. Shocks bloom and fade. Magnetic fields tie loops that tighten and snap. What begins as steady feeding can change tempo. A little more gas arrives than the disk can cool. Heat rises, the surface brightens, the spiral tightens. The star's light flickers like candle fire in a draft. Some systems hover here, indefinitely quiet thieves and quiet givers, recycling mass that will later be returned to space in winds. Others cross a threshold. The Eater is no ordinary star but a white dwarf, a core the size of Earth with the weight of a sun. On such a surface, gravity is strong enough to hold a thin skin of stolen hydrogen until the pressure rises. When it does, fusion ignites not gently but all at once, the way a field of dry grass can flame from edge to edge with a single match. Sometimes, the outburst is modest on cosmic scales, a nova that brightens and fades, leaving the dwarf intact for a future meal. Other times, the feast becomes a last course. Mass creeps toward a limit the dwarf cannot surpass, and the star unbinds itself in a thermonuclear supernova, so bright it can be seen across billions of light years. These type Ia explosions are clocks and yardsticks to cosmologists. To nearby space, they are gardeners, returning calcium and iron, silicon and nickel to the soil, from which later worlds will grow. There is a deeper hunger, too. If the Eater is denser, a neutron star with a crust like diamond and a core like a river of nuclei, or a black hole with a horizon and no surface, the menu changes. Matter torn from the companion dives into a steep well, heating into a ring so hot it shines in high-energy light before it vanishes. Sometimes, the companion itself is another compact object. Sometimes, the pair spirals together, losing energy to ripples in space-time, and the final embrace becomes a flash in multiple languages at once. Gravity's waves, gamma rays, infrared glow as newly forged elements cool. Kilinovae, we call those afterglows brief, red transients where the heaviest nuclei are made, gold and platinum among them, formed in neutron-rich sprays that drift outward like sparks from a whetstone. Webb's infrared sensitivity turns those embers into readable script, tracing the chemical birth of treasures we carry on our hands and wire into circuits. Between the first sip and the final flash, there are intervals Webb reads with a novelist's eye for change. Disks thicken, winds shift from steady to gusty, jets that once were narrow begin to precess, painting spirals into the surrounding gas. Sometimes the donor star swells into its red giant phase, and the pair plunges into a common envelope, two cores sharing one vast atmosphere, friction dragging them close. In that brief, luminous winter, angular momentum is shed, heat is shared, and the envelope may be flung out entirely, a glowing shell that cools into filigree. The survivors can be implausible, compact pairs that will merge in a future far off, stars spun up to millisecond rotation, oddities with magnetic fields strong enough to alter their light in ways that make spectra stutter and split. Failed cannibalism is not failure, it is variation, leaving behind relics that teach how orbits shrink, how mass loss shapes a system's later voice. If the quiet of night invites an accounting, you can make one that comforts. These feedings are not rare quirks that happen far away. They are a major way the universe moves elements around. A cluster of stars grows old, binaries tighten, novae pepper the decades. A supernova marks a century. In the outskirts, neutron star pairs harden and merge, each event a punctuation in the long sentence of chemical evolution. The heavy elements do not simply come from single massive stars dying in isolation. A measurable fraction is minted in these partnerships, in the tug and exchange, in the embrace and the breaking. When clouds later collapse into new stars and their disks, when pebbles become stones and stones become worlds, the ingredients were, in part, cooked in these kitchens. The fork clinks against the pot, and out into space goes carbon for atmospheres, oxygen for water, iron for blood. Feedback does not stop at chemistry. The light and shock from an outburst can compress a nearby cloud and set a cascade of star formation alight, or it can heat and stir a region so that collapse stalls for a while. A galaxy's star formation history is not a smooth line. It is a series of swells and rests, and binaries help set the rhythm. Webb's surveys, wide and deep, show this in aggregate. Regions with more compact mergers show different enrichment patterns. Places where novae are common glow differently in the infrared. It is not necessary to parse every instance to appreciate the mood. The universe prefers cycles. Matter climbs into stars, returns to space in flows and flashes, climbs again. On the timescale of sleep, it is a lullaby. On the timescale of galaxies, it is the difference between a thin, metal-poor disk and one seasoned enough to host rocky shores. From feasts of stars, the mind slides slowly, easily, toward ideas that sound like myth, until data begins to sketch their edges. The smooth fabric of space-time that general relativity draws so elegantly is a large-scale truth, the way a globe is a faithful summary of a mountain range. Up close, details matter. Under extreme stresses, subtleties appear. Webb's gift is not to measure gravity directly. Its tools are light and time, but to find scenes where geometry, energy, and matter push on one another hard enough that the approximations fray. In some strong lenses, brightness ratios refuse the simplest lensing maps unless we add small clumps of mass. In some cluster cores, heat seems to appear where the arithmetic of shocks, conduction, and cooling leaves a small debt. At some horizons, the colors of flares hint at particle populations that standard reconnection models would not predict without tweaks. None of this claims a new law. All of it marks a boundary, where current recipes need spices we haven't yet named. Physicists have words ready for such boundaries. Quantum fluctuations at the smallest scales make space-time a restless place, in theory, a foam of virtual excitations, but most of the time, on astronomical stages, that foam averages out. What Webb and its companions hint, gently, is that under certain conditions, strong gravity, dense fields, rapid flows, the small can lend its restlessness to the large. A patch of plasma near a horizon might amplify fluctuations into a flare. A filament under tension might tear and reconnect in a way that heats a cluster core more efficiently than a textbook would grant. A line of sight through a lens might cross a thread-like structure that perturbs light with a signature no ordinary halo can mimic. People call such threads cosmic strings when they model them, one-dimensional defects left from early phase transitions, like tiny cracks frozen into the glass of the universe. Whether the candidates now cataloged are truly that, or only clever illusions of mass and field, is a question for patient statistics and cross-checks with instruments that hear in other bands. For a bedtime ear, the point is simple. Even the smoothest music has overtones. Talk of vacuum decays and scars from the beginning can sound frightening in daylit prose. The night makes room for a softer view. Phase transitions are how a system finds a lower energy way to arrange itself. In a tea kettle, that means steam. In metals, magnetic order. In the early cosmos, the settling of fields into the values they wear today. If there are places where that settling left seams, they will be rare and faint, and the seams will be teachers of history, not threats. If there are events where the vacuum locally found a lower step, they will be embedded in a web of constraints that kept the universe broad and inhabitable for this long. The instruments are cautious. The papers read as they should, hypothesis first, mechanism next, predictions to follow, evidence to confirm or contradict. It is a comfort to watch science move at the pace of proof. Which brings us, drowsily, to a thought large enough to hold lightly, and only for a moment at a time. When distant disks tend to spin with the same subtle handness, when expansion looks a touch different depending on which yardstick you use, when black holes appear earlier than one narrow path would allow, a certain story suggests itself. Perhaps what we call the universe has a larger context, and perhaps some of its initial conditions reflect that context's properties. One picture paints our cosmos as the inside of a larger object, a black hole in a parent space, so that the rush of expansion we see is, from outside, a slow fall through a horizon. In such a picture, angular momentum from the parent would give our patch a faint rotational grain. Clocks and rulers might disagree slightly in ways that look to us like tensions between methods. Primordial black holes would be less surprising because seeds would be present from the outset. It is a working story, nothing more. Place it on the shelf beside others, universes born from quantum fluctuations, universes as bubbles in a larger field, universes cycling in long arcs of contraction and rebirth. The test is always the same. What does the story predict that the others do not, and can we see it? Do the alignments of spins persist as samples grow? Do time delays in lenses, added to other measures, ease or sharpen the expansion tension? Do the statistics of early black holes and bright little red dots bend toward the same parameter ranges in models with and without a larger context? The pleasure here is methodological. The tone stays even. Speculation is allowed to stretch its legs, then is asked to sit while observations vote. Fold everything back into the room where you are. The whisper of an air vent, the weight of blankets, the slow tide of breath. Far away, a white dwarf brightens and sleeps. Farther, a neutron star pair whirls and merges. Nearer, at the center, our black hole will flare again when a knot in the flow releases its stored tension. Between clusters, faint streams record old embraces. Through a lens, one galaxy's past and past and past appear like beads on a curved thread. Across it all, physics holds classical where it can, quantum where it must, making room for exceptions that are not rebellions but lessons. The universe is not breaking. It is teaching, patiently, in many classrooms at once. If there is a moral for the traveler at the edge of sleep, it is this: creation and destruction are the same circulation looked at from different seats. Stars feed and give back, elements rise and return. Space curves and shows us a face in four mirrors. Fields knot and unknot, sharing their warmth. Models strain and expand to include a new curve in the data. And through it, Webb keeps the lamplight steady on the text so our eyes can follow the line. Let your breathing keep time with that steadiness. Somewhere, another binary is beginning its slow exchange. Somewhere else, a filament is brightening at a hidden seam. Here, in this room, the only task is to drift carried by a cosmos that is busier and more generous than we had guessed, and yet gentle enough in its long rhythms to be a companion to sleep. Let the lights dim one more notch. What Webb has shown us is not a tidy syllabus but a night sky with new constellations of questions. The stories we carried, how galaxies grow, how black holes feed, how space itself stretches, were good first drafts. Then the mirror opened and the margins filled. Early giants blooming too fast, wanderers without hosts, filaments threaded with magnetism, lenses that turn time into a mosaic, hearts of galaxies flickering without a clock. None of it scolds us for being wrong. It invites us to be young again, to learn with wider eyes. It can feel unsettling to trade a garden for weather, a diagram for a dance. The universe Webb makes visible is busy and inventive, comfortable with extremes, patient with contradictions that only later reveal their kinship. Where we expected smoothness, we find texture. Where we expected a single road, we find several side paths meeting the same horizon. Even the largest ideas, subtle alignments of spin, seeds as old as the first light, hints that geometry itself carries a faint grain, arrive not as verdicts, but as working theories placed gently on the table, to be weighed by the next measurement. There is a quieter courage in this than in certainty. If reality is stranger than our models, then our task isn't to tame it with louder declarations, but to match its generosity with patience. We will keep listening for faint tidal streams that retell a cluster's history. Keep timing lensed echoes that turn gravity into a clock. Keep watching the Milky Way's center breathe in heat and light. We will let hypotheses travel with us. Some will fade at the first dawn. Some will stay the journey while the sky supplies new pages at a cadence set by stars, not by us. Isolation, too, looks different in this light. Whether our cosmos is a room in a larger house or a freestanding sky, the work is the same from here. Build instruments that make the dim legible. Share what we find. Let wonder sharpen, not dull, our care for one another. A universe that forges heavy elements in embraces and breakings, that knits new suns in the wake of what's been stripped away, that hides worlds in plain sight and then shows them again. Such a universe is not hostile to meaning. It simply asks us to make ours honestly with the raw materials it gives. So breathe with it. Somewhere, a jellyfish galaxy combs its tentacles across the dark, sowing blue nurseries in its wake. Somewhere, a pair of small worlds hums on radio pitches as they turn, keeping each other warm. Somewhere, a comet from another dawn glides through our sunlight and is gone. And here, in this room, the air settles, the heart slows, the mind loosens its grip. We are not owed comprehensibility, but we are offered clues, spectra and echoes, arcs and embers enough to keep going. The mirror will keep watch. The questions will keep arriving, softer now, shaped like lanterns along a path. We can follow at the pace of our breathing, learning to love a cosmos that refuses to be simple and yet is generous enough to be known a little more each night. When your eyes close, let them close on that. Not a final answer, but a steadying hush, a sky content to be vast while you drift, carried forward by curiosity and rest in equal measure.